So a system absorbs heat, its temperature is going to go up. And so that change in temperature we call delta T. The increase in temperature will be directly proportional to how much heat is absorbed. If twice as much heat is absorbed, the temperature will go up twice as much. So that proportionality constant, because the increase in temperature is directly proportional to the amount of heat, the proportionality constant is called the heat capacity, capital C. The italics and the parentheses run into each other there. Capital C. And the units of that are joules per degree Celsius or joules per Kelvin. So Q equals C times delta T. Q is proportional to the change in temperature, and C is the proportionality constant. So heat capacity, that C, is the heat required to change the temperature of a system by 1 degree Celsius. Now that sounds a little bit like the definition for the calorie, right? The calorie was the amount of energy needed to raise the temperature of 1 gram of water by 1 degree Celsius. And these units, if you take joules per degree Celsius or joules per Kelvin and you multiply by Kelvin or Celsius, then you end up with joules, which is a unit of energy. Well, the size of that heat capacity is important. So if the heat capacity is larger, then you're going to get a smaller temperature change for the same amount of heat. And the heat capacity of the object is going to depend on not only what the substance is, but how much of the substance you have. So if you think about heating a pot of water, you're going to make spaghetti. If you're going to make spaghetti for one person, you're going to boil a small amount of water. If you're going to make spaghetti for the whole football team, you have to boil a whole bunch of water. Does it take more energy to heat the larger amount of water? Of course it does. That only makes sense. You can boil a small amount of water with a small amount of heat. A large amount of water requires a large amount of heat. The amount of heat needed for the temperature change depends on the amount of substance. So that heat capacity is an extensive property. Extensive properties depend on how much of the substance there is. Mass is an extensive property. If you have more of the substance, the mass is greater. Intensive properties do not depend on the size of the object. So an intensive property is density. The density of a substance is the same no matter how much you have. So heat capacity is not all that useful. So what we use most of the time is called the specific heat capacity, C sub S, and this is the intrinsic capacity of a substance to absorb heat. This does not depend on the amount of substance. So the heat capacity of an object is also going to depend on the type of material. So it depends on how much substance, and it depends on what the substance is made out of. The specific heat capacity is the amount of heat needed to raise the temperature of 1 gram of the substance by 1 degree Celsius. So the difference between specific heat capacity and heat capacity, in the specific heat capacity, we're specifying how much, the mass of the object. And so this is going to have units of joules per gram degrees Celsius. We can also have a molar heat capacity where we're talking about 1 mole of the substance instead of the amount in grams, and that would be joules per mole degrees Celsius. Those are intrinsic properties. They do not depend on the amount of stuff that you're dealing with. So the equation that we need to become familiar with is this one, Q equals mc delta T. So this is the specific heat capacity, C sub S. A lot of times we leave the S off. Heat capacity is really just an idea. It's not at all useful. The specific heat capacity is what we always use. So please pardon me if I leave off the S. So Q equals mc delta T. And I sometimes call that Q equals MCAT, because that delta kind of looks like an A, right? Q equals MCAT. That's an equation to memorize. So here, the heat in joules is Q, the mass in grams, mass of the system, the specific heat capacity, and the change in temperature. And all of those units work out. So Q is in joules, mass is in grams, specific heat capacity is in joules per gram degrees Celsius, and let's make that at times. And the temperature is in degrees Celsius. And so the grams cancel out and the degrees Celsius cancel out, and joules equals joules. The reason specific heat capacity has these weird units is because then the units work out in the equation. So this is a table of some commonly used substances for these sorts of problems. In the CRC, which is that big fat book that we use to look up the density of water for one experiment, you can find pages of tables where people have determined specific heat capacities for different things, different elements, different compounds, and we're very thankful to all those people who did all that work and put it in the book. You do not need to memorize specific heat capacities. If you remember any of them at all, it would be the one for water. And I really wish they wouldn't do this. It's 4.184 joules per gram degree Celsius. So that one is useful. The rest of them, if you need them, they'll be given to you. This is the same number that is in the relationship for 1 calorie. 1 calorie equals 4.184 joules. So if we're looking at this table, here's water, and compared to these other substances, water's specific heat capacity is 4 joules per gram degree Celsius. All these metals have very low, and even sand and granite down here, come on, pointer, glass, these are all less than 1. Water has a very high specific heat capacity, and that turns out to be pretty significant. So this has huge effects on our weather. Water can absorb a lot of heat energy without changing temperature very much. And it can also release a lot of heat energy without changing temperature very much. So over on the coast, I think living here in the Central Valley where it gets just like mind-bogglingly hot sometimes in the summer, right? The coast usually does not get hot like that, right? Because there's this huge body of water called the ocean, and as the sun's rays come down and hit the ground and they hit the water and they heat things up, the water doesn't heat up as much as the ground does. And then at night, when the sun's energy is gone and the temperature of the air cools down, then the water radiates energy back into the air and it moderates the temperature. And so at the coast, they may have a 10, 15 degree change between the high and the low during the day. Here in the Central Valley, we can have a 40 degree temperature change, right? It can be 60 degrees at night and 100 degrees the next afternoon because there's not much water around here. There's very little in the air. There's not much in the ground either. We use water as a coolant in the engine of your car because it can absorb a lot of heat without changing temperature too much. It's used as in evaporative coolers because it will absorb heat from the air as it evaporates and cool the air. So water is really useful because of its high specific heat capacity. We've done problems where we used density to identify a substance because the density of a substance is an intrinsic property of it. An intensive property doesn't change with the amount. Heat capacity, specific heat capacity, is also an intrinsic property like that and can be used to identify things. So here's a lot of words. To determine whether a shiny gold-colored rock is actually gold, a chemistry student decides to measure its heat capacity. She first weighs the rock and finds it has a mass of 4.7 grams. She then finds that upon absorption of 57.2 joules of heat, the temperature of the rock rises from 25 to 47 degrees Celsius. Find the specific heat capacity of the substance composing the rock and determine whether the value is consistent with the rock being pure gold. We can calculate from this data the specific heat capacity of her rock and then compare that to the specific heat capacity for gold. So we're going to need that Q equals MC delta T equation. So Q equals MC delta T. What we're trying to find here is the specific heat capacity. So that's the C. So we rearrange this equation. The specific heat capacity is going to equal Q divided by M times delta T. So we need to identify what Q is, what M is, and what delta T is. So as we look through the problem, the first number we come to is 4.7 grams. That's the mass. So that's M. M is 4.7 grams. Absorption of 57.2 joules of heat. That's Q. Q is heat. It's absorbing 57.2 joules. That's positive because the heat's coming in. And then the temperature change. So they don't give us the delta T, the change in temperature. They give us the final temperature and the initial temperature. So we have two temperatures. We have 25 degrees Celsius. And we have 47 degrees Celsius. One of those is the initial, one's the final. Which is the initial temperature? The 25. So that's the initial, and then the final is the other one. The words are telling us that. From 25 to 47. So this is the initial, this is the final. To find delta T, it's always final minus initial. So this would be 47 degrees Celsius minus 25 degrees Celsius. And I'm pretty sure that's 22. A temperature change can be positive or negative. A positive temperature change means the temperature went up. A negative temperature change means the temperature went down. And so the sign is important here. So there's our delta T. So we can put these values into this equation. So Q was 57.2 joules. Divided by the mass, 4.7 grams, and divided by the change in temperature, 22 degrees Celsius. So 57.2 divided by 4.7 divided by 22 equals 0.55. Some of our numbers only have two significant figures, so we'll round that. Actually, I'm going to stick it up here. And we're going to get 0.55. The units, joules, grams, degrees Celsius, nothing cancels out. So you just write them down. It's joules on top, grams, and degrees Celsius in the denominator. And those are the units of specific heat capacity. So there's a specific heat capacity. Is it gold? Well, we have to look. We go to the table, and we find gold. And gold has a specific heat capacity of 0.128. Is this gold? Not a chance. So, not gold. Any questions? What would be an easier way to find out if the rock was gold?
Well, melting point.
You do melting point, but that's going to... Density. The density would also give us. I mean, the melting point would be helpful, and looking at physical properties. Melting gold, though, requires a lot of heat and a very high temperature. Finding the density of it, you could do very easily with a balance and a graduated cylinder and some water. Right? But then we wouldn't have the problem to do. So. Any questions? So we've talked about heat transfer happens between two objects that are at different temperatures. And the heat will flow from the high temperature to the low temperature until they both become the same final temperature. The amount of heat lost by the hot material is equal to the amount of heat gained by the cold material. So we can look at it this way. So here we have a beaker of water, and the water has an initial temperature of 25 degrees Celsius. We take this block of metal that's hot. It's 55 degrees Celsius. We put it in the water. It's like the opposite of an ice cube, right? You're not putting something cold in the water, you're putting something hot in the water. This has more internal energy than the water does. And so it's going to transfer some of that energy in the form of heat to the water. And that transfer will keep going until the metal and the water are at the same temperature. Exactly how much that temperature changes depends on the mass of the water, and it depends on the mass of the metal, and it also depends on the specific heat capacity of the water and the metal. The heat that the metal gains or loses is equal to the heat that the water gains or loses. The sign is opposite. So if Q for the metal is negative, then Q for the water is a negative of a negative, which is positive. So Q for the metal equals negative Q for the water. So Q for the metal is mc delta T, so that we've got the mass of the metal and the specific heat capacity of the metal and the change in temperature. And that's going to equal negative times mc delta T for the water. Now, you can't have a negative mass, and you can't have a negative specific heat capacity, but you can have a negative temperature change. So we can do a problem like this. A block of copper of unknown mass has an initial temperature of 65.4 degrees Celsius. The copper is immersed in a beaker containing 95.7 grams of water at 22.7 degrees Celsius. When the two substances reach thermal equilibrium, the final temperature is 24.2 degrees Celsius. What is the mass of the copper block? And again, I'm thinking, well, wouldn't it be easier just to stick the dumb thing on a balance? But then we wouldn't have this problem to do. Okay, so sometimes it's helpful to draw a picture. So there's my beaker, and I've got some water in it. Actually, let's use a lighter blue. So I've got some water in it. And let's write down what we know about the water. How much water, what's the mass of the water? 95.7 grams. And what's the initial temperature of the water? 22.7 degrees Celsius. So we put the copper in a beaker containing this much water at this temperature. So we've got the copper. So we'll make that this little block, and it's kind of coppery colored. So there's the copper. What do we know about the copper? It has an initial temperature of 65.4 degrees. So its initial temperature is 65.4 degrees. Do we know its mass? No, that's what we're trying to find, right? Where does this 24.2 come in? That's the final temperature of what? Of both of them, right? They come to the same temperature in the end. So the final temperature of the copper equals 24.2 degrees Celsius. And the final temperature of the water, I don't have room for that. Final temperature of the water also equals 24.2. So could we calculate the change in temperature for these two things? Sure we could. So delta T for the water. I'm using colors here, but if you're just using one color, then you'd need to write subscript water or W or something so that you can tell them apart. So the change in temperature for the water is the final minus the initial. So that's 24.2 degrees Celsius minus 22.7 degrees Celsius. I don't trust my head on that one. 1.5. For the copper, it's the same type of calculation. The change in temperature for the copper is its final minus initial. Final temperature is the same, 24.2 degrees Celsius. But the initial temperature was different, 65.4 degrees Celsius. So 24.2 minus 65.4 equals negative 41.2 degrees Celsius. That negative sign is important. What that tells me is the temperature of the copper went down. It lost heat, its Q will be negative. The temperature of the water went up, its Q is going to be positive. Okay, well, what we can say here is that the mass of the copper block times the specific heat capacity of the copper times the change in temperature for the copper has to equal negative mc delta T for the water. The heat lost by the copper is gained by the water. They are equal in magnitude but opposite in sign. So we know some of these values, right? We know the delta T's, so I know both of these delta T's, and I know this M, but I need the specific heat capacities. So I need the specific heat capacity of water and of copper. Well, specific heat capacity for water is 4.184 joules per gram degrees Celsius. For copper, though, I got to go look that up. So here's copper, 0.385. So this is 0.385 joules over grams degrees Celsius. Got those from a table. So I've got this equation here. I can solve this equation for the mass of the copper. The mass of the copper is going to equal negative mc delta T for the water divided by C delta T for the copper. So now I'm going to plug my numbers in. So I've got a negative sign, and then I need the mass of the water, so that's 95.7 grams. I need the specific heat capacity of water, 4.184 joules per gram degrees Celsius. I need the change in temperature for the water, 22.7 degrees Celsius. And then I have to divide all of that by the specific heat capacity of copper, 0.385 joules per gram degrees Celsius, and the change in temperature for the water, which is negative 41.2 degrees Celsius. You can't just ignore that negative. There's a negative here, and there's a negative down there, and they're going to take care of each other because we can't have a negative mass. If you come up with negative mass, then something went wrong in your calculation. Yeah?
Wouldn't the change of temperature for the water on the top be 1.5 degrees Celsius?
Thank you. Yes. What was I thinking? Thank you very much. Yeah, I don't know where I got that. A little distracted today. I think I was just looking down here and pulling out numbers. That happens. I see people do that on their tests and stuff too. Here's the change in temperature. Thank you. So now we just, let's double check our units here. So if we look at the units, we've got grams and grams. I'm going to cancel there. And joules are going to cancel. And degrees Celsius cancels, and degrees Celsius cancels. And what I've got left here for units is 1 over grams. So that's the same as grams. So I've got negative 95.7 times 4.184 times 1.5 divided by 0.385 divided by negative 41.2 equals, so this equals 37.864 sig figs. This temperature change only ended up having 2 significant figures, so thus only has 2 significant figures. The unit is gram, and so we're going to round this to 38 grams. Any questions? The math here is not complicated. It's adding and dividing. It's multiplying and dividing, and then there's a little bit of subtracting, right? The tricky part is keeping track of all of it, right? So you have to write things down clearly so that you can see what's going on. I would not try to write this part down without writing at least some of the rest of this down. And I do this for a living. I wouldn't do that. I would write a few things down. So you need to write more things down. Any questions? So there's heat, and now we're going to talk about work. There's different kinds of work. One is called pressure volume work. And this is caused by a volume changing against an external pressure. So if we have gas in a piston expanding, so here we have a small volume and we're expanding it, we're pushing the piston out. The piston, unless it's in a vacuum, has some pressure around it, atmospheric pressure at least. And so there is a force involved in pushing this out. So there is a volume change here. And the volume change will be the area times the change in the height. So the gas expands. The change in volume is going to be positive. It gets bigger. But the system's doing work on the surroundings, and so the work is negative for the system. So this type of work equals negative P delta V. It's the pressure, the external pressure, times the change in volume. The negative is here to get the sign correct. This is the system doing work on the surroundings. And this is the sort of work that happens inside of an internal combustion engine. So in the pistons in your car, you have these small explosions that expand the volume and push a piston down against a force or against a pressure. And then your car translates that into forward motion. So W equals negative P delta V. So now we get into some weird units, because if the pressure is in atmospheres and the change in volume is in liters, how is that a unit of energy? Well, there's a relationship between joules and liter atmospheres. Come on, pointer. It's right down there. I can't point down there, but for some reason I can write down there, so I will do that instead. I will give you that conversion The tricky thing is remembering that it exists, okay? Because it's not an intuitively obvious thing. How does an atmosphere and a volume, a pressure unit and a volume, how does that make energy? Well, it's this pressure volume work. A cylinder equipped with a piston expands against an external pressure of 1.58 atmospheres. If the initial volume is 0.485 liters and the final volume is 1.245 liters, how much work in joules is done? So we've got some numbers here. Let's write them down. 1.58 atmospheres, and we've got 0.485 liters, and we have 1.245 liters. So this must be a pressure, right? Atmosphere is a unit of pressure, and it says pressure of, so that's a clue too. This is the initial volume. So I'm going to call that V sub I for initial. And then they tell me that this is the final volume. Okay, I labeled the numbers. And we need that equation, work equals negative P delta V. Because. So I need pressure, I need change in volume. Well, delta volume, same pattern as delta T. Delta volume is the final volume minus the initial volume. If the change is positive, that means the thing gets larger in volume. If the change is negative, it gets smaller. So the final is 1.245 minus the initial 0.485 . 0.760. That's the change. I want this 0 here at the end because each of these in my subtraction had 3 decimal places, and so my answer should have 3 decimal places also. So we're looking for work. Work equals negative pressure, 1.58 atmospheres, times the change in volume, 0.760 liters. Hello? Okay, so the result there then is, my calculator is showing me negative 1.2008. And the units would be atmosphere liters or liter atmospheres. We usually say liter atmospheres. Significant figures would be 3, but the question wants how much work in joules. So I need to convert liter atmospheres to joules. And so we're going to use this conversion factor right down here. 101.3 joules is 1 liter atmosphere. There they did atmosphere liters. Fine. Show me up. 101.3 joules. So I'm going to multiply, so I get joules on top and liter atmospheres or atmosphere liters on the bottom. 101.3 and 1. So I take my number and I multiply by 101.3. So I'm going to get negative 121.64 joules. I still have 3 significant figures, and so this is minus 122 joules. The system, the cylinder and piston, did 122 joules of work on the surroundings. Any questions?